Hello, everyone, and welcome to Lecture 1E. We're going to start in a little bit of an introduction to the kinetic theory of gases. So this is continuing on some of the things that we had talked about in some of the earlier sections. We talked about how pressure is created by gases, and we've talked about the concept of an ideal gas. And really, there's five postulates that went into the creation of the idea of an ideal gas, some of which we've talked about already. One is that gas molecule size is negligible. Whether it's an atom, whether it's a molecule, it's negligible compared to the size of the vessel that the gas is in. They move in straight lines at different speeds, so they don't take curved paths. They move just in a straight line until they collide with something. Any intermolecular attraction is negligible, so the molecules don't interact with each other. They might collide and bounce off. When they do collide and bounce off, those collisions are elastic, meaning that no energy is lost, and so they might change direction, but they won't necessarily change speed. And the kinetic energy is proportional to temperature. So in looking at kinetic energy, we want to look at molecular speeds. We were looking at vapor pressure earlier, in an earlier section, and we said that some molecules may have enough kinetic energy in order to escape whatever particular phase they might be in, whether they're in a solid, whether they're in a liquid. They may be able still to turn into a gas. And if you look at kinetic energy, the only components of kinetic energy are mass and velocity. Well, the mass of a molecule can't change because the composition must remain the same. So the velocity must be different. And so this leads us to that postulate that molecular speeds within a sample are not the same. Instead, they exist as a distribution of speeds. And we call this the Maxwell-Boltzmann distribution. And we can see here, as we go through at a fairly low temperature here, we peak at a fairly low speed, and you can see most of the molecules have a fairly low molecular velocity. If we go to 1,000 Kelvin, we're a little bit more spread out. You don't have as many molecules bunched up at a low speed. Instead, they're here. And then if we go to an even higher temperature, 2,000 Kelvin, then they're really spread out. And you can see you have significantly higher molecular velocities at 2,000 Kelvin. You can see that, as we just mentioned, that distribution is dependent on temperature. Now we can calculate a thing that's called a root mean square speed, which is essentially a very fancy average. And we do this by factoring in the molar mass of the gas and the temperature that the gas is sitting at. And so here's our equation. So the Greek letter mu is equal to, and that's our root mean square speed, it's equal to the square root of 3 RT over the molar mass, where R is our gas constant, T is temperature in Kelvin, and NW is our molar mass. Now, the thing that we have to look at with R, we use the energy version of R because we're looking at speeds, 8.314 joules per Kelvin mole. Now, the joule unit doesn't really factor much into speeds. However, we can break the joule unit down into its components, which is kilogram times meter squared per second squared. And there we see that we've got units of meters and seconds. And so those are the units that we want for speeds. And it's meter squared per second squared. We also have a square root sign in there. So that will allow us to get to meters per second with a proper unit analysis. Now notice also in the joule unit, the mass unit is kilograms. Well, our molar mass generally is grams per mole. However, when we're using the root mean square speed formula, we have to express our molar mass in terms of kilograms per mole rather than grams per mole. All that means is you're taking the molar mass in the way that you would normally express it and divide that by 1,000. So rather than 50 grams per mole, it would be 0.05 kilograms per mole. So it's just something you have to remember when you're using this equation. And here we can see a variation of velocity distribution with molar mass. We see that as molar mass goes down, our speed increases because we have a molar mass of 2 a molar mass of 4, a molar mass of 18, a molar mass of 28, and a molar mass of 32 up here with O2. And so for the given amount, same amount of kinetic energy, the lighter the mass, it would make sense that you're going to have higher velocities with lower masses. And so you have a higher velocity distribution with molar mass. And these would be for samples at the same temperature. And so obviously if you change the temperature, in addition to changing the molar mass, you're going to have a little bit more complicated system. Now here's two terms that are often used interchangeable, and they are somewhat related, but they are not the same thing. So we'll look at the differences between these two terms, diffusion and effusion. So diffusion is the process of one substance spreading out to occupy a space. In terms of gases, they always occupy a space uniformly. So even if they have a point source, they will spread out from that point source and then occupy the space uniformly because they travel until they hit something and then continue to go. So you can think about scents or smells. So something like maybe a bottle of perfume or an incense, something like that, where you have evaporating molecules interact with your nose, so like a perfume. So when we look at how quickly molecules are moving, so they're moving at hundreds of kilometers per hour, and yet perfume from someone takes some time to reach your nose. If they're sitting, 3-4 meters away from you at hundreds of kilometers per hour, that shouldn't take very much time. And yet it can take a little while, or maybe somebody has some food and it takes a while for you to smell it. But why does it take so much longer than what it seems like it should if they're moving that fast? Well, the process of diffusion is really a study in chaos. Molecules travel in a straight line until they collide with other molecules. And there's a lot of other molecules in the air. You might just be regular air molecules, nitrogen, oxygen. There's obviously other small molecules in there as well from all kinds of sources. And when they collide with those other molecules, it can change their path, maybe back to where they were coming from or an entirely different direction from where they started. And so molecules can't really get from point A to point B in just a single straight line. They take a very chaotic path to get from point A to point B. They'll probably get there eventually, but sometimes it can take quite a bit longer than you might think. Now you might say, well, maybe if we increase the temperature, we'll increase the speed, and so we'll increase the rate of diffusion. And while it's true that the temperature will increase the speed that the molecules are traveling at, that high rate of speed will also lead to an increased number of collisions because all the other molecules are still in the same places. And so increasing temperature actually has little effect on the rate of diffusion of gas molecules. Now, if we look at effusion, effusion is the process by which a gas flows through a tiny hole. And when we say tiny hole, we mean very tiny, like molecule-sized, atom-sized. So something that is just very, very small. A really good example of this is to think about balloons losing their gas. If you've ever had a helium balloon, especially if it's a latex balloon, you fill them up and they're great, they float around, and by the next day they're sitting on the ground just seriously deflated from what they were the night before. And this is because the latex molecules actually have fairly large pores in them, and helium is a very small atom, and it's very easy for that helium to escape through that latex and go off into the atmosphere. So effusion is controlled by molecular weight or the molar mass of your gas. And true rates of effusion become really difficult to study because the pore sizes of the material are not constant. The different materials have different distributions of pore sizes. There's just far too many variables. So in order to try to eliminate all those variables, what we generally do is study effusion rates of different gases within the same environment. So we eliminate the environmental conditions, and that way we're just looking at the effusion rates under a certain set of conditions. So let's compare a balloon that's filled with helium compared to a balloon that's filled with air. Now, we might ask ourselves, how does air have a molar mass? Well, it has an average molar mass. It's mostly nitrogen and oxygen. And when you factor in the different mole fractions and their different molar masses, you can get an average molar mass of about 29 grams per mole for air. And so we're going to set up the following proportion. We're going to say that the rate of effusion is proportional to 1 over the square root of the molar mass. And that's the equation that we use. Notice that we don't have an equality there, but we can compare those two rates. They're two proportionalities. So we can say that the rate of helium effusion over the rate of air effusion is going to be equal to the square root of 1 over the molar mass of helium over the square root of 1 over the molar mass of air. And so if we get rid of those fractions inside, we end up flipping what's on the numerator and what's in the denominator. And so we have the square root of the molar mass of air over the square root of the molar mass of helium. And we end up with the square root of 29 over 4, so 2.69. And what this essentially tells us is that helium will effuse under the same set of conditions. Helium will effuse 2.69 times faster than air, which is something we might expect when we compare how long it takes a helium balloon to go flat as opposed to a balloon filled with air to go flat.